In this video, we're going to be looking at the last section in Chapter 11, using geometric probability. Now, geometric probability is just like any other probability that you've ever calculated in math. It's just going to have shapes and figures. So probability is an event, or probability of an event is a number telling us how likely the event is to occur. So probability is always a number between 0 and 1. It can be a decimal or a percent. And here's how you find probability. It is the number of favorable outcomes over the total outcomes. Now, I like to think of this as the part that you're looking for over the whole. So the part over the whole. Now, geometric probability is going to be a ratio that involves a geometric measure such as length or area. So probability and length is probably the easiest of the geometric probability problems. And it says let AB be a segment that contains CD. So here you can see AB, and CD is part of AB. So you can see AB is the whole. It says if point K is chosen on segment AB at random, then the probability that K is on CD is the ratio of the length of CD over the length of AB. So again, it's the part over the whole. So if I were to draw K anywhere on here, here or here or here, it's going to be a probability of this length over this whole length. Now, looking at problems from this, we're going to focus on number 1 first. It says find the probability that the point chosen at random on LP is on MN. So this is the part while LP is the whole. So the first thing we need to do is to figure out what exactly we need to do. So we're going to do part, the length of MN, over the length of the whole, which is LP. Now we can see by the number line that this is 3 units. And if this goes from -2 up to 10, that's going to be 12 units. So this is going to reduce down to 1/4, or as a decimal, that is going to be a 0.25 or a 25% chance of the point being located on MN. Now, this next one, it says find the probability that the point chosen at random on FJ is on a given segment. Express your answer as a fraction, decimal, or a percent. We are just going to stick with percent on this. So let's just do percent. Now, the first thing here, we need to figure out how long FJ is. So that's the very first thing. This is at -5, and this is going up to 7. So that is going to be a 12. -5 to +7 is 12 units. Now, GH is going to be from -1 to 3. So 1, 2, 3, 4, 5, 6. Except this is -3, not -1. Sorry about that. So this is going to be 6 units over 12. And that, of course, is going to be 50%. Now, HJ is 1, 2, 3, 4 out of 12. And 4 out of 12, of course, is going to be 1/3, which is going to be 33.3%. And then FJ, well, FJ is the whole thing, so 12 over 12 is going to give us 1, so that is going to be 100%. So typically, probability and length, again, that's the easier problems of geometric probability. You're just going to do part over whole. Now, probability and area is where we'll spend most of our time here. So probability and area. It says let J be a region that contains M. If a point K in J is chosen at random, then the probability that it's in the region M is the ratio of the area of M to the area of J. So this is the part out of the whole. So sometimes the figures can be a little tricky though. So it says find the probability that a randomly chosen point in the figure lies in the shaded region. So for these first two problems, we're going to kind of walk through them slow, and we're going to talk about the part and the whole. So the very first thing we always kind of like to do is the whole. So we have this circle here. So the area of this circle is going to be pi r squared. And this is going to be, looks like a 16 is the diameter. So this is going to be pi 8 squared. And for calculation purposes, it is easier to leave things exact with pi as your answer. So the area of that circle is 64 pi. Now, in order to find the shaded region, we need to find the area of the square so we can subtract that out. So the area of the square, we're going to have to do a little bit of work. So since it is a square and this is 16, okay, this is going to be 8, this is going to be 8. And if I draw this here and here, that's going to be another 16 because that'll be an 8 and an 8. So if you remember back when we did the area of a kite or a rhombus, there was a formula, 1/2 times the diagonals. We're going to go ahead and just do that there. So if I take 1/2 of 16 times 16, we're going to get 128 units. Now that is not the only way to find the area of that square, but it certainly is the quickest way here. Okay, so remember, half the diagonals multiplied together. Now the area of the shaded region is going to be the circle subtract out that square. Okay, so that's going to be the area. Again, I'm not going to use decimals yet because they're too hard to write down. Now this is going to be the part where the area of the circle is the whole. So now I have expressions for both of those. So part area over the whole area. Now these 64 pi's do not cancel out here because they're connected with a subtract. So we're going to have to do this on the calculator. So it is on the top 64 pi, subtract 128, divided by, again, use parentheses on everything or use the fraction key, 64 pi. So I'm going to get 0.36 for the probability. So the probability is about 0.36. Now I always like to see if my answer is reasonable. So does that look like, 36% of that circle? And I think that it does. Now, figure 2 here, number 2, we have a hexagon. It is a regular hexagon, and 2 of those are shaded. So the total area, okay, and we're going to do this one highly simplified, okay? The total area is 6 triangles, and I am not going to find the area of those triangles because the shaded area is 2 of those triangles. So it doesn't matter what the area of those are, I know the probability of this. And you could just count. This would almost be like a kindergarten problem. 2 shaded out of 6. So we can literally say the part that is shaded over the whole that is shaded is simply 1/3. Those 2 is 1/3 of that. So this is approximately 33.3% or 0.33 if we're doing a decimal. So sometimes we can just get by with looking at it, especially if it is just a regular shape. Now, moving on to the back, we're going to do 3 and 4, I believe. And on number 3, the first thing I want you to notice is that it is a rectangle with 2 identical circles, and we need to find the probability that it's in the shaded region. So the first thing I'm going to do is I'm going to find the whole area, or the total. I can do that quickly because 4 times 3, so that is 12. Now the next thing I need to do is I need to find the area of the circles. If I can find the area of the circles, that's going to be the part that I subtract out. And I can find the area of the circles if I do 2 times pi r squared. Well, we're going to have to figure out the radii of the circles. Well, it's kind of easy because if this is 4, then this is 4, then that means each of these diameters are 2 which means the radius is simply going to be 1. So this is simply 2 pi times 1 squared, so it's essentially 2 pi. Now, the probability of this is going to be the whole subtract out the part, now that is going to be the shaded part, over the whole part, which is simply 12. And again, we're going to use the calculator to calculate this for us. This time I'm going to use the fraction key, so I can show you a different way to do it on your calculator. It is 12 minus 2 pi divided by 12. And that's going to be approximately 0.48. Again, look to see if that answer is reasonable, and I think so. It looks about half what the circles are taking up, and left over is about 0.48. Okay, now the next one, we're going to have to put everything that we know together, because for once we are now dealing with this regular hexagon, and we are given a radius of the circle and the radius of the hexagon. So we may have a little bit more work to do for this one. So the first thing I'm going to do is I'm going to find the total or whole area of the circle. That is pi radius squared. So that is going to give me 49 pi. Now the hexagon is going to take a little bit more work, because we're going to have to subtract that hexagon out. From yesterday's lesson, we know it's half the perimeter times the apothem, but we have a problem. We don't know the perimeter and we don't know the apothem, but we can find those. So I am going to simply extract one of these triangles out. We know this side is 7. We know this side is 7 because it's the radii. We also know if I drop this, this is going to be the apothem. And since it is a hexagon, this angle right here, if I do 360 divided by 6, this angle right here is 60 degrees. So this angle right here is going to be 30 because it's half of 60, and this angle right here is going to be 60. Now we have a 30, 60, 90 triangle. The hypotenuse is here. We always know opposite of the 30 is half of that hypotenuse. And we also know the one opposite of the 60, in this case is going to be the apothem, is 7 square root 2 times square root 3. Okay, so now, if using that information, if this is 7 halves and this is 7 halves, then what we know, this right here is going to be 7. So the perimeter of the hexagon is going to be 42. Now this is the two pieces of information we need for this formula. So area equals 1/2 the perimeter, which is 42, times the apothem of 7/2 square root 3. Okay, now to kind of keep this exact, it's kind of best to do that. We're going to do exactly that. We're going to say 1/2 times 42 times 7 halves. And that's going to give me 73.5. So I'm going to actually express that as a fraction. And we're going to say that this area is 147 over 2 square root 3. It's just easier to write that down than to write the decimal down again. So now, time to find the probability. Okay? So the probability is going to be the part that is shaded. That is going to be the circle. Subtract out the hexagon over the whole area, which is the circle. Now, for this one, I'm going to do in 2 steps. So the first thing I'm going to do is I'm going to do the top. 49 pi, subtract, again, I'm going to use the fraction key, 147 divided by 2, square root 3. I'm going to do that first, then I'm going to divide that by 49 pi. Okay, so that means the probability is approximately 0.17, about 17.3%. Again, if you look at that picture, that looks about right. There's not a lot of parts that's shaded there. Now, just for time's sake, we are going to actually skip 5 and 6, and then we're going to move on to question 7. It says a sector of a circle intercepts an arc of 80 degrees. A. Find the probability that a randomly chosen point on the circle lies on the arc. And then B says the probability that it's in the sector. So this is bringing together arc length and sector area. So the first thing, we're going to draw a picture. We're going to draw this 80-degree arc here. I need you to know that this is talking about just this line, okay? Now for the next one, I'm going to draw the same circle. This is the 80%, but in this one, it's going to be asking the probability that it's in the sector, not on the circle, but in the sector. So for this one, we know that this one is 80 degrees, and we know what's the whole circle. So for this one, it is just 80 degrees out of 360 degrees. If we type that in on the calculator, we have 80 divided by 360. We're going to get a 0.22. So we're going to say about 0.22. Okay? Now for this one, what's interesting for this one, this is, the around the circle, but for this one, this here is 80% of the circle. So this one is 80%, 80 degrees of the whole circle. Well, the whole circle is 360. So what's interesting is it's the same answer, because you can see here and here you get the same thing. Now, perhaps the most famous geometric probability problem would be the spinner. So question 8 says, use the spinner to find the following probabilities. So you have a probability of landing on a purple. Well, you can see here, this is 120 degrees. So this is going to be approximately 120 out of 360. So this is going to be approximately 1/3, so 0.33. And of course, that's rounding. Now this next one, the probability of the pointer landing on red. Well, you can see red is here. This is about 20 degrees out of 360. So if you do this one on the calculator, you are going to get about 0.05. So 5/100ths. And we really could round this one, but we're just going to put a line over it saying that it goes on forever. So recapping geometric probability, I just always need you to think about what you know about circles or shapes or regular polygons, and you're going to be doing part over whole.